Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Good morning, good afternoon, good evening. This is Roy Simpson, professor of mathematics, Cosumnes River College, Sacramento, California. And this video is the next one in a series, haha, pun intended again, covering sequences of series for pre-calculus. You should have just watched an introduction to infinite series, and now we're going to talk about infinite geometric series. As I mentioned in the series video, that finding formulas for series is very challenging. In fact, nigh on impossible. However, summations involving arithmetic sequences and summations involving geometric sequences have patterns. And specifically, geometric sequences, summing them up, if you do it off to infinity, in other words, sum up an infinite number of terms within that sequence, it has a chance to converge. It's not that it will converge, it has a chance to converge. So let's see why that's true. Actually, let's just make the statement. If your common ratio is less than 1, strictly less than 1, so in other words, in absolute value, so that means that your common ratio cannot equal 1, but it can be negative, it can be positive, it could be 0, well, that'd be silly though, but it's some number between -1 and 1, not including -1 and not including 1. Then the infinite geometric series based upon that geometric sequence converges to A over 1 minus R, where A is the initial value of the geometric sequence and R is the common ratio. If that is not true, in other words, if the common ratio is equal to 1 in magnitude, or if its absolute value is greater than 1, then it will diverge. The series will. The summation, the infinite summation will diverge. So let's go ahead and prove this. So we do know that S sub n from our last video, was it the last video or it was 2 videos ago, partial sums of geometric sequences, that if you have a geometric sequence, its partial sum is given by this, right? So all over 1 minus r. A times the quantity 1 minus r to the nth, all over 1 minus r. First of all, if r is equal to 1, we've got an issue. If r is equal to 1, you're dividing by 0. So r cannot equal 1 by virtue of division by 0. Of division by 0. But if you think about it logically, if r was equal to 1 anyway, you would essentially be adding a to itself over and over again. Because remember, this series is a plus a to the first, or ar to the first, plus ar squared, plus ar cubed, and so on and so forth down the line. If r is equal to 1, you're just adding a to itself an infinite number of times. And obviously that's going to blow up. So that is not going to work out. So, all right. But by virtue of division by 0, it would also, at least the summation formula would not work. And I give a stronger justification down below. So that the series would sum to a plus a plus a plus a plus a on forever, which is not a finite number. Now, if you let r equal -1, so I'm taking out the edge cases basically, then we'd have the following situation where our summation would be k equals 1 to infinity of a times -1 to the k minus first, which would give me a minus a plus a minus a plus a minus a, and it would go on forever. It alternates between a and -a. Now you might say, but look, these two cancel, and so do these two, and so on and so forth. And you'd be correct, they do cancel. But because this goes on forever, you do not know when it stops. And it could stop when you're at a or at minus a. So it could be, the value of this could be a or it could be 0, basically. And because of that, You can't determine what it's going to become, and this will diverge. This does not converge to a finite number, so this is not equal to a, nor is it 0. So it doesn't converge. It doesn't converge to something in between. Now, I'm a little bit hand wavy here, but the reality is it doesn't converge. Okay, so it diverges at the edges. And by the way, I have to be somewhat hand wavy here because you're not in calculus, so I cannot actually prove these, but I can justify them strongly. So let's say that r in magnitude is greater than 1. Notice I'm taking care of all the cases where the theorem says we'll have divergence. This theorem only says we'll have convergence of the infinite sum if the magnitude of r, the absolute value of r, is strictly less than 1. And I already took care of the case where r is equal to 1, where r is equal to -1, and now I'm considering what if the absolute value of r is greater than 1. So I'm taking care of all the spots where we'll have divergence, because they're kind of easy, honestly. So if the magnitude of r is greater than 1, then our partial sums, which is equal to a times 1 minus r to the nth over 1 minus r. Well, as n goes to infinity, r to the nth will also go to infinity because it's a number, the absolute value of which is greater than 1. So if you just think about numbers like that are greater than 1 in magnitude, it could be 1.2. Okay, if you have a number like 1.2 in for r, and you let the power get massive, that number will be huge. If you have a number like -1.2 and you raise it to a massive power, that number will be huge. So because of that, this partial sum will approach either plus or minus infinity. It'll basically blow up as n goes to infinity. And honestly, it doesn't actually have to go to plus or minus infinity. It could just bounce back and forth between very large values. But the reality is this r to the nth power is going to get massive, and it'll get out of control as you keep adding more terms to your series, and it'll just get wild. So again, I can't use calculus here, unfortunately, but the reality is that as n gets massive, r to the nth gets massive as well, as long as r is greater than 1. You could test that out, by the way. Grab a calculator or something like that and try a value of r like, I don't know. Let's say you have something like let's just do that, 1.1 to the 100th power. If you do 1.1 to the 100th power, that's not even, by the way, the power is not even infinite, right? It's not even anywhere near a huge power. But that number is approximately already 13,780. And that, by the way, is just one term you're adding. You're adding a bunch of these terms. The next term in line will add 1.1 to the 101st power times a. So 101st power. And so these numbers just blow up. So that's why this gets massive. So we get divergence. And I just wrote it that way. In this case, that summation would not be finite because it'd just keep blowing up, or it'd waver back and forth between a huge positive number and a huge negative number. But the one I really want to focus on is, what if the absolute value of r is strictly less than 1? Well, this requires a little bit of calculus too, actually, or calculus as well. So if the absolute value of r is less than 1 in magnitude, then as n runs off to infinity, r to the nth actually approaches 0. And you could test this out. In fact, let's go over to Desmos. I think this is a good application for Desmos here. So here we are at Desmos. I've just created a 20-term sequence. The sequence is just going to plot the n value, 1, 2, 3, 4, and then r to the n minus first power. So this is basically our sequence that we're looking at. If r is less than 1 in magnitude, here is the plot of the values. So watch what happens as you increase r. It really still does, notice it's less than 1 in magnitude, it still does tend to 0 as time goes on, the y values do. And you could go back to negative values as well. So let me hop back here to negative values. We'll go to negative 0.1, negative 0.2. You can see it does spread out a little bit, but it's still tending to 0 as time goes on. I can make my list a little bit larger. So let's go to 200 here. And you can see that as time goes on, it definitely does still go to 0. But what if I instead want my list, or my R value, my common ratio, to be equal to 1? Well, then your sequence is always equal to 1. And remember, you're adding these values together. So you're adding 1 plus 1 plus 1 plus 1 forever. What if you have this? R is greater than 1. Well, look what happens to your sequence. It blows up. And you're adding these values together, by the way. So it's obviously going to blow up. And same thing in the negative direction. If you go to negative 1.1, same thing will happen. It'll blow up actually in 2 directions, and you're adding these values together. It gets out of control. So that is sort of a justification as to why when you're between negative 1 and 1, the sequence values will converge and your series will also converge. So, and I should have had the series on here, but I just didn't. So reiterating what I just stated, if the absolute value of r is less than 1, then as n goes to infinity, r to the nth, r to the great power, goes to 0. Now remember, our summation, then, our nth summation, which is equal to a 1 minus r to the nth over 1 minus r, as n goes to infinity, remember that r to the nth is tending to 0, and so this tends to, green, right? Tends to a times 1 minus 0 over 1 minus r, or in other words, a over 1 minus r. And while it is not really a great proof, because you need calculus, the reality is it's a pretty darn good justification that our series converges to a over 1 minus r, as long as the absolute value of r, the common ratio, is less than 1 in magnitude. Now, I really think this is where it's at. Geometric series, infinite geometric series is where you want to be at this point in pre-cal. You want to get to really know these, get really good with them, and establish a dominance with that so that you can be great in your calculus course. So let's go ahead and find the sum of this infinite geometric series. They already gifted us with the idea that it's an infinite geometric series. All we need to do is find a formula for the actual sequence, not the series, but the sequence. So when you're handed a series like this, just in a number form, your first step is, what the heck is a sequence, right? So let's go ahead and do this. Remember, if it's geometric, the geometric sequence should be of the form a sub n, which is equal to a times r to the n minus first. Remember, a is the very first term of your sequence, and they've given us our sequence. It's 1 over 3 to the 6th. Next term would be 1 over 3 to the 8th. The next term would be 1 over 3 to the 10th. Obviously, the next term would be 1 over 3 to the 12th, and so on and so forth. So we know our very first term is going to be a. Actually, I'll write it on the other side. But then we need the common ratio. What do I multiply by to get the next term in line for our sequence? Well, it looks like I'm multiplying by 1 over 3 squared, or basically 1/9. And it is true. I'm just adding 2 powers of 3 every single time to the denominator. So that's what our common ratio is going to be. Once I know that, I have everything ready. I know that my geometric sequence is going to be a, which is 1 over 3 to the 6th, times 1 over 9 to the n minus first power. And we want to add those up forever and ever and ever. First thing I need to note, and this is critical, the absolute value of the common ratio, which is 1/9 in this case, is less than 1 in magnitude. And once I know that, I know the geometric series, the summation of all of these terms off to our right forever and ever and ever, sorry, off to our left, forever and ever and ever, these will converge to something. So this series, I'm going to write it this way, summation k equals 1 to infinity of 1 over 3 to the 6th times 1/9 to the k minus 1. That should equal, according to the previous theorem, the a value over 1 minus r, because our common ratio is less than 1 in magnitude. So let's go ahead and insert the a value, which is our initial value. That is 1 over 3 to the 6th divided by 1 minus, and we'll insert the common ratio, which is 1 over 3 squared. I'm writing it that way for a very specific reason. I'm going to multiply both numerator and denominator by 3 to the 6th. That's why I wrote that 9 as a 3 squared. And you get this beautiful 1 over 3 to the 6th minus 3 to the 4th. I trust you can do the simplification there. And I'm going to actually factor out 3 to the 4th and be left with a 3 squared minus 1. Notice I'm doing something that you would do with algebraic expressions. Nothing stops you from using your algebra with constants. 3 to the 4th is 81. And 3 squared minus 1 is 8. And 81 times 8, 80 times 8 is 640. So 648. So 1 over 648 is the sum of that sequence. Didn't think you could actually do it, right? But you totally can. That's the beauty of geometric series and geometric sequences, is that if your common ratio is less than 1 in magnitude, and if you want to add up your sequence forever and ever and ever, you totally can. The value's very, very nice. It's a very nice formula. It's just the initial value divided by 1 minus the common ratio. You do have some arithmetic in there, but I assume you know how to do that. So that's pretty awesome. And here we are with another infinite geometric series. Again, the same idea is we need to list out the terms. I just always do this because I think it's very important. So I'm going to list out the terms: 1, negative 1/2, 1/4, negative 1/8, and so on and so forth down the line. And this 1 is our initial value. And all we need to do is find out, what do we multiply by to get to the next term? Well, obviously we multiply by a negative 1/2. You need to double check that multiplying that by a negative 1/2 will get you to positive 1/4, which it does. Just double check that multiplying that by a negative 1/2 will get you to a positive 1/8, or a negative 1/8. So it does. So we know our common ratio. And also note, again, the common ratio that we just found, which is equal to the absolute value of the common ratio, which is equal to the absolute value of negative 1/2, is less than 1 in magnitude. That's going to be important because we want to add these values up forever and ever and ever and ever, all the way down this list here. So let me write out the formula for the sequence first. A sub n is going to be equal to the initial value, 1, times the common ratio, negative 1/2, raised to the n minus 1. And what this summation up above is the summation of our series from n equals 1 to infinity of 1 times negative 1/2 to the n minus 1. It's the summation of our sequence. And we know, because again, the magnitude of our common ratio is less than 1 in magnitude, or common ratio is less than 1 in magnitude is what I should say. We know that that is going to converge. It will converge to a over 1 minus r. A in this case is 1. That was our initial value. 1 minus, and the r is negative 1/2. Multiply top and bottom by 2, and you'll get 2 over 2 plus 1, because of negative negative, and that'll be 2/3. So if you add this series of numbers up forever and ever and ever, it will eventually converge to 2/3. It's a convergent geometric series is what we would call that. So really, really cool stuff. That all of a sudden dealing with geometric series opens up a whole new world of mathematics to us. And finally, in this video at least, we're going to play with decimals. Because how in the world does somebody write this as a fraction? Well, it's actually not too terrible. You just have to know placeholders, place values, I guess. So what I'm going to show you is the general idea behind it. So when you see a pattern, and the pattern in this is the 5, 6 on forever, what you're going to do is write the rest of that decimal off to the side. So that decimal off to the side is 2.13 plus 0.56 on forever. And then you're going to start to convert things to fractions. Specifically, 2.13, that is the hundredths place. And before anybody yells at me, I totally just saw, once I said hundredths place, that we're not adding 0.56 on forever. We're adding 0.0056 on forever. Please don't yell at me. So 0.00 and then 56, this pattern will start to repeat on forever. I had to take advantage of the fact that these two zeros were there. So yeah, sorry about that. So anyhow, converting to 2.13, noting that the last digit is in the hundredths place, that'll be 213 hundredths. That's how I know how to write that as a fraction, is just noting the last digit's decimal place. And you say, oh, if that's a hundredths place, then it's that number 213 over the hundredths. If it's the thousandths place, it would be that number over 1,000. Now what I'm going to do is I'm going to break apart this 0.0056 to a plus 0.0056 plus a 0.000056 to a plus 0.00000056 plus ... down the line. Now, it looks pretty ridiculous, but the reality is that's exactly what that number is. If you were to hold these over each other, maybe I should write that out. So if you wrote 0.0056 and you wanted to add to that 0.000056, and you wanted to add to that a 0.00000056, you would see, and you keep that going forever, that it would be a 0.00565656565656, right? It would just go on forever. So that is the pattern. That's how you write it out initially. Don't worry, we're going to get to a fraction in a moment. And this is equal to, again, that 213 100ths is just hanging out up front. But now I'm going to write this as a 56 over. This is 10 to the, this is over 10 to the 1, 2, 3, 4th place. Plus, this is 56 over 10 to the 1, 2, 3, 4, 5, 6th place. The next one, plus 56 over 10 to the, you probably guessed it, 8th place. You can count though, 1, 2, 3, 4, 5, 6, 7, 8th place. You're counting where that 6, that pattern ends, right? And this is actually the sum of a sequence. It goes on forever. These last three terms plus the rest on the back end are the sum of an infinite sequence. And let me showcase that off to the right-hand side. Your sequence would be 56 over 10 to the, I forget what it starts at, 10 to the 4th. The next term in line would be 56 over 10 to the 6th. The next one would be 56 over 10 to the 8th. The next one would be 56 over 10 to the 10th, and it would just keep going. That sequence of values, its initial value is this. And every single time, all you're doing is multiplying by 1 over 10 squared. Again, multiplying by 1 over 10 squared. Again, multiplying by 1 over 10 squared. That's all you're doing every single time. So this is our common ratio. Again, I'll note the common ratio, its absolute value, is the absolute value of 1 over 10 squared, which is 1/100th, which is less than 1. That's going to be critical because I want to add these values up, as you can see in black here. I want to add these values up forever and ever. So I'd like the common ratio to be less than 1 in magnitude. That 213 over 100 is still going to hang out front for a bit. Plus. But now I can easily say that my formula or for my geometric sequence is a sub n is equal to the initial value, 56 over 10 to the 4th, times the common ratio, 1 over 10 squared, raised to the n minus first power. That's the sequence I've written down right here. So that's what I'm going to plug in as a series here. It's a summation from n equals 1 to infinity of the initial value, 56 over 10 to the 4th, times the common ratio, 1 over 10 squared, raised to the n minus first power. Now I can just, because I know the common ratio is less than 1 in magnitude, I can trade that out for the formula a over 1 minus r. So let me go ahead and do that. This plus the formula a, which is the initial value, over 1 minus the common ratio. Now notice it's really compressed all this down. Now you might be thinking, why would I want to write that as a fraction? The reason why is because it's a use. That's all. So all I'm going to do here is multiply numerator and denominator by 10 to the 4th power on this guy. And you'll see this just takes a little bit of practice. You'll be great with this. You will be. It's really not terrible. You just need practice. Whoops. 213 over 100 plus 56 over 10 to the 4th minus 10 squared. And 10 to the 4th minus 10 squared, let's go ahead and do that same, well, actually, I don't need to do that same trick I did last time. 10 to the 4th is 1 with 4 zeros behind it. That's 10,000 minus 100 is 9,900. So we have 213 over 100 plus 56 over 9,900. And to combine these fractions, I'll just multiply that first fraction by 99, both top and bottom. So 99 to the numerator and 99 to the denominator. And you'll get the following. I just have a calculator next to me. So 213 times 99 is going to give me 21,087 over 9,900 plus 56 over 9,900. Now I can just easily add 56 to that other numerator there, and this will be 21,143 over 9,900. And I guarantee that if you grab a calculator, that will be 2.13565656 on forever. That's a really good use of this geometric series, infinite geometric series. In the next video, we're going to do applications of geometric series, which is actually the best thing to watch. So for now, watch this several times until you get this expressing the repeating decimal as a fraction bit, because that ends up being somewhat important. All right, have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.